Let's let's see. You want to? You guys have any questions about the homework? That is it? Yeah.
We was having trouble for E figuring out like what exactly the Q temperature means.
Let's see. The theta temperature.
Oh, it's theta.
Yeah. So that's the
Okay.
yeah. All right. Q in symbol font is theta. So if you have it, if you just copied it over, yeah. So you know, so you know what that is, right? Theta. Yeah, that's just that plot I showed you that where it crosses over. So that's I guess this is a low molecular weight you expect to see like the structural effect, and then at high molecular weight they interfere with each other and it straightens out. That's it. At high molecular weight, then the chains, they're like balloons that inflate up when they touch and they'll squish to be straight. That's the idea. So whatever that is. Where's that? It's right here at this point. Yeah. Anything else on that? On the homework or?
Obviously, in B, and I think that's where's this like maybe like other equations. So like with that, because I like looked at B, but I didn't understand B enough to understand the plot.
What was it about B?
So we have to like look at like the other extensions and compare how they like got those derivations.
Yeah.
And I came to the conclusion that because our current like research like paper is trying to like understand like different terms, such as like that with like radius opening and stuff, that they have to adjust like the equation in order to like have variables that like make sense. But then I didn't understand how to go from like I didn't understand like C at all. Like how to explain if like that equation was right or like how that correlates to van der Waals.
Okay, so the van der Waals here. I mean, I think to me there's an error in the paper. Yeah. So um, this one, so the van der Waals. So B2 for van der Waals is B minus A over T. So, and this is the excluded volume. So you have, it's the next sphere has a region where it can't go. But in fact, that region's excluded. So it's this is a B0. They calculate it, it should be 8 times B0. It's a volume one marble, and then it's going to be 8 times that excluded. That's that thing. So you can calculate that number. This number allows you to have phase separation. So it's like somehow these things will attract to each other. So there's an attractive potential that effectively reduces the speed. And if that potential, so KT is making these things fly around, that attractive is making them come together. So you have a balance between like flying around and coming together. That's that term, right? And that impacts like the apparent, let's like the apparent excluded volume. So you have the actual excluded volume, and this potential of attraction is going to make it seem smaller because it makes it look as if it pass through the thing. And so if you say that the apparent excluded volume equals 0, that would be ideal. That's an ideal gas that things can actually pass through each other. An ideal gas has no excluded volume. And so when that equals 0, that's an ideal condition. And then this temperature becomes like the ideal temperature or the theta temperature. And that's going to be A over B. Right. So in our case, A is going to be like, or this is going to be 1/2 minus chi. So it'll be like a 1/2 minus chi in the term for A, and B is excluded volume, something like that. So So everything goes back to the van der Waals thing, which you can get this from, if you say P is RT over V, right? So molar volume, so you have no N. And then you say there's excluded volume, and then you say there's minus A over T, minus this potential. Oh, A times rho squared, A divided by V squared. So rho equals 1 over V. The molar density is 1 over the molar volume. So there's a T there, there's no T in that one. So if you take that and you say P PV over RT is the compressibility factor, which would be 1 for ideal gas. It's going to be that, it's going to be 1 plus rho times V2, because 1 over V is rho. So this would be a term of like rho into rho squared. So that's the binary interaction term, the excluded volume term. So if you compare these two, right, there's a slide that does that. It comes up with this equation. There's a couple slides that do that. So anyway, so that's the van der Waals. That's VW. Right? So that's the basis. Van der Waals is the basis of everything when people talk about interactions of things. Anything like polymer coils, balls, anything. So that's going to be like the first step. That's the first time we had a model that had a cartoon with it. The other ones are like, maybe just do this power series expansion, the viral expansion. There's no cartoon with it. It's just like binary interaction. But this thing can also be, it's not spherical, it's elliptical. So it could be a lot of things other than binary interaction. So van der Waals is the first thing we have to put a handle on, like what's going on. And then so everything builds off that. Anyway, so his equation for nu, which is I think in the supplemental thing, isn't that equation, it's a problem. So he gives an equation that looks pretty good because it's got this theta minus T minus theta over theta.
You swap that.
Oh, sorry, I haven't found it, but right. So here, so this guy, so nu here is B2, and nu 0 is small b from the van der Waals, like the actual hardcore excluded volume. So theta by theta is 1, so that gives you b, and then minus, well, this term, so this term should be a over t, not t over theta. It's upside down, right? Like theta is 1, that gives you b. V0 is b. Then you have V0 times minus V0 times T over theta. That should be 1 over temperature, net temperature. Right. So you would find a different critical temperature from that. It would be actually the other way around, I guess. It would be like B over A instead of A over B. So that can't be right. So anyway, he just throws this out, maybe written as, I mean, I'm not sure he actually uses that, but basically that isn't right. That's the point of that question. I think it isn't right. So this business of, because he's considering, so the last part, do you get that? Like why they have to be spaced? Those balloons can't be touching. Otherwise he's not, because he's using random coil calculations, and once they touch, they get stretched out. But that's kind of the slide here. That becomes a brush. So that's like this thing. So people draw it like this. Like you have, if the A distance, so the yellow line up between the chains attached to a surface, and then if the coil size is larger than that spacing here, then they'll stretch out like they're shown stretched out here. Right. So that his thing assumes that they're random coils, so you can't have them stretched out. Like that whole derivation with the third Weyl coefficient, second Weyl coefficient, all that assumes you have an ideal coil. You can't have like coils touching each other. So, and then D, you said D too, right? is a fairly obtuse frequency function at the bottom of the page. So this is the Purcell equation. Right, so that's linked here. Okay. Oh, the link doesn't work because sometimes you just copy the link for the wiki and it ends up with this character. Some weird thing. Guess it doesn't get dash or something. That should be dash. Anyway, so this is the equation. So you have the pressure, you have the flux, the flow, then R to the 4, you have pi viscosity, mu's the viscosity. So you have R to the 4 over viscosity. And then his equation, so he's got R to the 4, and then he's got the pressure. And then it's basically his frequency. This front end of this term is Purcell's law. Like if you just kind of look at that, really, oh, here. So if you just look at this equation and rearrange it so that you can get Q, the flux, he explains in the supporting how the flux has to do with the frequency. In other words, the particles have to flow through a tube. In other words, the polymer chain has to flow through a tube. So it's tube flow, which is Purcell's law. And the rate of them flowing through, the frequency, is going to be proportional to the flow rate through the tube. Right, so Q is proportional to F. And then you can, if you rearrange this, you get R to the 4, you get kind of those terms, like these R to the 4 and the pressure driving force, right, which is delta P. He just uses P, but, anyway, P and delta P, I guess, are swapped out. Then if you wanted to, you could say, what is K? So just all the rest of the terms in the Purcell's law is what K is. So just take all those, that's K. It's going to have the viscosity in it. It's going to have the tube length. It's going to have 8 pi in it. It's just tube flow he's using. Then he's got this weird exponential term that behaves the right way, but I don't really know where that came from. So you can try to figure it out from what he said. It describes the whole thing in the supporting information, but I kind of lost track of where this exponential term came from. So maybe you can figure it out, or you can just say that's because it isn't really a tube flow, it's some kind of polymer squeezing through a thing or something. Right, so, but anyway, the front end thing, when you see R to the 4, and then Purcell's law is the first thing you learn in transport. It should be absolutely the first thing you learn. It's from the 1800s, right? So it's like, that should be the first thing you know. So you see R to the 4, that looks like a weird function. It's not squared, it's not cubed. So where did the 4 come from? And you realize that's this guy's thing. So, and then it has something to do with flow. So you can just say like it isn't so strange. Like in other words, the trick here is to like look at, he's throwing this thing out and you're like, wow, that looks really weird. And then you notice this is a sequence that should go through your brain, with your training. That, wow, that looks really weird. I have no idea what that is. Oh wait, R to the 4, that's Purcell's law. Oh, there's a P in there too. So that those terms are from Purcell's law. And the frequency, he says, has to do with the flux through the tube. And this is just Purcell's law, and then I can figure out what K is. I can predict how K behaves. So then you have a little bit warmer, fuzzier feeling about what he's doing, versus I have no idea what this is. So that's kind of where you should get to, like, look at something. So your train of thought should be like, everything I know, how does it match up with what he did here? And then like, it won't happen every time, but basically at some point that'll be a nice feeling, I can figure out what he's doing. So anyway, any other questions on this thing? It's more or less just, it has to do with what we're in class, so it's kind of nice. Yeah, it's actually, there's a video of the things flashing, right? So he has a video of what happens. So he's got a UV light coming in. And once the DNA strands come out for a while, what do they call it? They saturate, like, so they don't emit fluorescence anymore. So they only fluoresce the first time the UV hits it. So they're going to come through, and they don't fluoresce on the other side of the membrane. So they come through the little hole, and then immediately they get zapped and they just blink. And you can see it in the video. So the frequency is like how often does he see the blinking, counts them, and time. Yeah, yeah, he's mimicking translocation across a membrane. That's what he's trying to do. And he's trying to say, in that case, you have like a protein that will, well, some of the proteins actually make pores, but the inside of the pores have things dangling off that react with the thing that is supposed to go through and reacts otherwise with things that aren't supposed to go through. So it's a controlled kind of port. So this is directly copying that. Like he's directly copying transport through a membrane, right? So through a biological membrane, with the hope that he can use it to filter DNA or filter viruses or something, but yeah.
So that second part is the exponential term coming from the diffusion through the, I guess the supersonic chambers and all that.
I haven't really thought about it much. That sounds like a pretty good track to take. Yeah, I mean, anything like that, you get extra points. If you just say what you just said, that's probably like 5, 6 extra points. Right? You know, I mean, just think about it. I don't really know. Yeah, it's got to be some kind of like energy. Exponential is usually like energy over KT. There's no KT in here, so it's not that. The Debye screening stuff has an exponential in it. So I don't know. I'd start fishing like that, you know. But basically what you said sounds fine. It'd be nice if you could say like, here's this flow function that has an exponential in it. That with pressure as an argument. You know. So yeah, actually it's the same argument. It's the same as the front end. So it's like the cell. Yeah, it's like the Q from Purcell's law. It's like exponential the Q. So if this argument in the middle, this is 1 over that thing, right? So if the flow, so flow is high, so this is 1 over the flow. So when the flow is low, this number gets smaller because it's negative exponential. When the flow is high, this number gets larger. Anyway, so that doesn't tell you anything. This kind of enhances the frequency. From Purcell's law, you get an added flux from this thing. I don't know why. It definitely goes, the front term and the back term both go in the same direction with pressure and with the radii things. So, oh wait, yeah, no, it's the same thing upside down exponential. You could also take this and say exponential of x is 1 plus x squared over 2. So you do an expansion of it. So you could say this is really 1 plus 1 over the flow rate, 1 minus 1 over the flow rate. So you have the flow rate here times 1 minus 1 over the flow rate. So when the flow rate gets low, that kind of distorts the thing or something. I don't know. There's a couple of ways you could do. Exponential, the expansion is always pretty useful to look at, you know, but usually. So anyway, I haven't answered that one, so you can mess around with it. But basically anything you say would be good. It shows like you have an active living brain, you know, versus just a recording machine type thing. So even if you're wrong, you know, it's good to say something. So, all right, so is that anything else on this thing? I think it's okay. So, all right, so we can get rid of that. So I wanted to go into this this business of, so we went through the collapse transition, and the idea was that it was like you had a piece of plastic, like we used to take dry cleaner bags, tie knots on them, and light them on fire on the bottom, and they would they kind of crumple up in the middle. So the middle part goes to like goes to a 3D structure, and the coil itself is a random walk. So you have a 2-dimensional, like when you get to the theta temperature, it goes to 2D. So it's a random walk. And then within that random walk, you have these kind of things clumping up into 3D. So it makes a string of 3D clumped up pieces that are in a random walk. And as the temperature drops further, the clumped up pieces grow larger. And eventually the whole thing is a 3D collapsed coil. Right. So basically that's kind of the cartoon of what's happening when the thing coil collapses. So it doesn't happen at a discrete transition. It's happening like small scale growing to larger scale, right? So So anyway, that's not the only thing that does that. And that wasn't the first thing that they found that did that. So the thing is, like anything that's molecular weight dependent, if you look at pieces of the polymer, the molecular weight is smaller for small pieces and larger for larger pieces. So the rules change on this thing that way. Okay, so the simplest one, so the first one says there's 5 things that do this: temperature, concentration. This is, let's see. No, there's 5 things. There are these 5 things somewhere here. Here. So you have force. If you pull a force on the chain, it goes through that transition. So that's the simplest one. Temperature does the same thing. Concentration also makes these things. And then if you think about it, the Kuhn length of the step length itself is a transition. So you have the chain fully straightened out at very small scales, and then it goes into this random coil. And that's really a balance between KT, moving the chains around, like the bonding strength of the bonds of the helice or something of the chain of the charges along the chain that make it straighten out locally, right? So it's a balance between forces. Because the thing is so big, like at small scales, it would just be a rod, but at large scales, it becomes this random walk, right? So that's the idea. So there's a balance between those two things. So all these things like that, and this collapsed coil is like that too. Like in other words, because the molecular weight is smaller, it's easier for it to crumple up. And at larger scales, KT takes over and it makes a random walk for the collapsed coil, right? So that means that everything you do to a polymer chain introduces a new size. That's the theme of this. Like you do something to the polymer chain, it introduces a new size. So the simplest one, so the size that it introduces is called a blob. So you can have different kinds of blob. You can have a tensile blob, thermal blob, but sometimes called thermic blob, concentration blob, the Kuhn length, which is kind of a blob, and then this collapsed coil blob, right? So there's different kinds of blobs. What it means is you've introduced a size scale transition in the system because the molecular weight's different for the different parts. And the molecular weight has different effects. So it can explain things like the radius of gyration gradually changing with temperature. Like it doesn't all of a sudden have a step change from an expanded coil to a Gaussian coil. It doesn't have a step change to a collapsed coil. In the same way with concentration, there's a gradual change to a theta condition from a good solvent as you increase the concentration. So this allows you to have a cartoon of what's going on, and from that you can predict things like what's the size of the coil. Right. So that's kind of the theme here. The simplest one is this tensile blob thing. So the idea is that you have so let's see. I brought this thing because I was looking around my office for something like this. Anyway, I'm not sure how this will project, but if you take something like this, right, you can't have entanglements to this. These things like naturally just entangle a bit. So if you start out and it's a random coil and you start to pull it, so it forms a line, but within the small scale, it's still a random walk. Right. So and I pull it harder and harder, and those random walks like pull out. Because the lever arm at a large scale is larger than the lever arm at a small scale. So the force that you apply might be put throughout the chain, but because of a smaller length, that it doesn't straighten it as easily. Right? So you have a larger lever arm, then the higher the force, the more finally it'll just be fully straightened out. You got no kinks left. Does that work? It's like a 3D problem, actually. You can see it better in 3D. But anyway, so that's the idea of the tensile blob. It's like a simple, really simple idea. Where it has application is in the same problem, like tethering chains to surfaces, and then the chains get straightened out, right? And also, if you have a star polymer or a dendrimer, so they make polymers where you have grow a chain and there's a branch, and then you grow a chain and there's another branch. So those are called generations of a dendrimer. You end up with a kind of a colloidal particle that's all these tree branches going out, right? So in a system like that, I don't know if I have a picture of that, but that's called the Dowd-Cotton model, where you go through this kind of business of straightening out the chains, right? So it's kind of similar. So this idea of straightening out the chains was popular, and this guy Pincus more or less figured this out. Yeah. Oh yeah. All right. All right. So we had before. So if you have a Gaussian chain, and then you define the energy by comparison. So it's going to be the probability of finding an end-to-end distance R is going to be Gaussian, right? And the most probable is at 0, and then it decays down with a bell-shaped curve, right? So then if you say Boltzmann energy, it's E over KT. This is thermally driven, so it has to, both these have to apply. So that means the energy you can get from that argument of that, which is this thing. And then if you have the energy, the derivative of the energy with distance is a force. This force times distance is energy, right? So then you can get the modulus of the chain, this thing. Right. So that's drawing a chain, but the chain has to remain Gaussian. It can't be like straightening out like the headphone thing, right? So anyway, if you do straighten it out, then you can say like, basically you can say that the thermal energy is going to make it want to go random, and the force wants to make it straighten out, and you get this tensile blob size from that. The size of transition where it would, below this size, it's going to be Gaussian because KT dominates, and above that size, it'll be a straight line where the force dominates, right? You can get that. Somehow you can get that, but anyway, that's kind of just an argument of temperature versus force and how that results in size. Like force times distance gives you size. KT is what's making this happen, so there has to be a size like that. So I think I did that more elegantly before, but I think that's good enough. Anyway, this looks a lot like these other things, sizes that come out like the Beaucage length. So that's the size where you go to mean field. So if you talk about correlations and you have a correlation function, and then it goes to a mean field at long distances, so where you see the forces of charges, two charges interacting, and then the KT force kind of randomizing the charges. So they'll organize below the Beaucage length. That's the idea. So you're going to like kind of crystallize below Beaucage length. And that's also has something to do with KT, except here, KT, the higher the temperature, the smaller the Beaucage length, because the KT kind of eats up the charges that are making things organized. Whereas KT is proportional to the length here, because KT, the larger KT, you disorganize, you disrupt the chains. I mean, you disrupt the lengthening of the chains. Right, so they're opposite temperature dependence. The same idea, you're balancing temperature for a random process with some kind of organizational process. The organization here is external, like you apply a force, the organization here is internal. Right, so they're opposite in temperature dependence because one's internal, this one's internal and that one's external. You apply a force externally, apply charges internally. Right, so there's kind of a similarity between this tensile blob and the Beaucage, and also kind of between the Debye length. But the Debye length is a little bit more complicated how the temperature dependence goes. So the idea with the Debye length is just that you have these counter ions coming in that interfere with the charges. Right. So there's a third party. There's two charges that are affecting each other. And then there's this other charge, the counter ions, N, and they have charge E squared. And in that case, the idea is that the counter ions form a cloud around the charges. And as the temperature goes up, that cloud like disperses kind of. So that means at the higher temperature, that means the feeling of the charges, the Debye length is where you don't feel the charges anymore. So the charge feeling gets larger with temperature. It's complicated. Right, so you have to think about this as a cloud of counter ions to figure out what the temperature dependence of this is. And the cloud expands, making it more dilute. You can also make it more dilute by dropping the concentration. Both have the same effect. They increase the Debye length, this distance over which you feel it. Anyway, there's a direct analogy between these charge length things and this tensile blob idea. Right, you have this KT versus the force that you apply to it. Anyway, so this is what you do with something like that. So what you want to know is how big is a chain? Like so you have this situation, how tall is this pillar that you make? That's one of the things you want to know, right? In other words, how many of these tensile blobs are there within the chain? And then how thick is my layer that I make? Like in this problem of the tube, like if he wants to clog the tube, he needs to know that this length of these chains is half the tube diameter, and then it clogs it. Right. So how do you calculate that if what you know is the molecular weight of the chain and the and basically the force that's pulling on the chains. Right, so, or if you can measure the length of the height of the chains, what was the force that, effective force that draws it out, that doesn't really exist, that's created by the other chains pushing on it on the side. But, I mean, there's different ways you can kind of look at this, but anyway, so if you have that, you say this thing below the tensile blob size, it's going to be a Gaussian chain, so it's going to be n all squared. And the number of units within that is a molecular weight of the chain divided by the number of tensile blobs that you have. So n by n tensile times the Kuhn length squared gives you the tensile blob squared. That'll be like r squared for a chain. So r squared is n all squared, but within the blobs, within these tensile blobs. And then you can rearrange that and find out how many tensile blobs you have. So it's going to be like n all squared divided by tensile squared. And then the length of the chain, so the distance, the height of this thing is going to be r, and that's going to be how many tensile blobs times the tensile blob length, right? And we know that tensile blob length is 3 kt over f. And then the number of tensile blobs is this expression, which also has 3 kt over f in it. So you just plug those all in, and you get the thickness as a function of molecular weight and a function of the force and kt, and you know the Kuhn length. Right, so some goofy little model, and you can get something that might be useful on it. So that's called a scaling argument. In other words, there's no prefactors here. It just gives you the trend of this thickness. If you double the molecular weight, I double the thickness. Right. If I double the force, I double the thickness. If I double the temperature, I get half the thickness. I mean, in absolute temperature. Right, so that's kind of like the theme of this. This is the simplest case, right? So you just have kind of a simple cartoon, and then you just end up with the thing that you want from the parameters that you have. This is kind of the standard of how Polymer physics went in like the 70s and 80s. Like everything was this kind of scaling thing. Right? So anyway, so but you can get pretty powerful predictions from that. Like, in other words, things that really work, and then you can use them. All right, so the second one is this concentration blob. So you have, let's see, where's that table of all the things? So you can just go through them, like, actually they aren't in order. So tensile is okay. Concentration is like the next simpler one, you know. So if you have oops, here. So we have this thing C star. So that's the concentration within a coil, a Gaussian coil. In this case, it's self-excluded volume coil. So you have molecular weight of the coil divided by r squared gives you the concentration of the coil, right? And then r goes with the end of the 3/5 if it's an expanded coil. So that gives you 9/5, and that ends up giving you C star's end of the -4/5. That means if n is big, then C star is small, and if n is small, C star is big. So you have some concentration the system is, and then you have this moving target of the C star. And there's going to be some point where the concentration equals C star at some n, and that's going to be the n for one of these blobs. If you go to smaller n, then the coil's expanded coil. And if you go to larger n, the coil's a random walk, like a collapse of a Gaussian coil, theta coil. Right, so you go expanded at small, and then Gaussian at large. So it's on a large scale, it's dense. At a small scale, it's expanded, which is kind of hard to visualize. So something like you have a wall and it's made of like foam bricks or something. And if you look at it from far away, it's like a solid wall, it's 3D. But if you go into it, it's not 3D. It's got these kind of foamy bricks that compose it. So something like that. So anyway, that's basically the idea of the concentration blob. So from that, so let's see. So you can do the same kind of scaling argument for this thing. So you have C star is this thing, and then let's see. So we have the blob size. So at small scale, it's going to be this good solvent scale. So you can say, all right, so you can say, instead of using the concentration, like reduce it by this C star. So when you get to C star, this thing's 1, and then you get the Gaussian coil size. So R is the Gaussian coil size, or the excluded volume coil size. And then this is a number, then you say it's going to be a power law dependence, because everything in polymers is power law dependence. So then you can say R depends on 3/5 of the N. That's expanded coil. And then C by C star is this 4/5 thing. So you have 3/5 from this, and then 4 times P divided by 5 for this concentration blob size. All right. So then you say, well, if you're above the overlap concentration, then nothing can depend on N because you can't see N. Right. So how that works is, see, this is slide what, 14. Let me remember that, because I want to go ahead here somewhere. I think it's in, oh, no. Wait, it's in the other slide. Sorry. There, escape from this, escape from that. We go to the other PowerPoint, this thing. So this is the way it works. If you have one chain, okay, and then you get to C star where the chains just touch, right? And then you get above C star, well, you can't see a chain anymore. It's like counting sheep. A postdoc did this. So you count sheep. So if there's one sheep, you can count them. When you get a lot of sheep, you can't see a sheep. You can see that it's made up of fur, but you can't see a sheep, right? So, and you get to really concentrate, you can't see anything. In terms of scattering, so you have the power law where you see it's a fractal at the large end, low Q, that's the coil size. At the small end, that's kind of like the Kuhn size, and this would go power 1 for a polymer. Right, for this thing that's drawn, it would be 4 because it has a surface. Then as you increase the concentration, there comes a size where you can't see it anymore, and then it goes flat because it just looks at larger size, just looks the same, right? You don't see anything different. You see the concentration, but you don't see anything else. You don't see the structure. As the concentration goes up, so this is intensity divided by concentration, because the intensity goes up proportional to concentration. So you lose, so there's a size scale where you lose, it's basically the size of the white that you see here. It's a correlation length for the system. You lose the size of the thing, you gain the correlation length, right? And then that, as you increase concentration until you get to the concentration of one of these, and then it just reaches that and just kind of game over at that point. It's like totally fills space, right? So you'll see a diminishing return on the scattering. I mean, normalized scattering by concentration as you increase concentration, and you lose the possibility to measure what the thing is. Here you can see what the thing is when you're in dilute. Here you can't see it anymore. But you get this new number, you get the screen length, or the concentration blob size, and then you also get something about how these things interact with each other from that intercept, the low Q intercept. So that's kind of, these are some data that shows that. This is intensity divided by concentration. Then going up in concentration, you can see exactly that happens to the data, right? So this blob size is something you can measure. You can get that thing there. Anyway, so anyway, so this is the blob. That's the blob we're talking about. So this concentration blob. So we have, all right. So we have that this thing, because you're above the overlap concentration, then you can't measure the molecular weight anymore. You can't see it because it's not there, right? It's already entwined, so you can't see. Like if you have a shirt, you can see it's a shirt, but you can't see the fibers in it. You can't say how long is a fiber in that shirt. But if I rip the shirt apart into fibers, you can measure the fiber. So if it's dilute, you can measure it this way. You can't see, right? So this thing can't depend on N at all. So this number has to be 0. If that number has to be 0, then you solve for P and find out it's 3/4. Then you can predict the blob size. And once you know the blob size, then you can predict the coil size as a function of concentration. Right. So then you can get R should go with concentration to the -1/8 power. Right. So that's kind of an important thing to know if you want to know how the coils change in size with concentration. Right. They're going to follow that dependence. So, and this also, all right, so this can also be used to predict some other things. I'll show you afterwards, but basically that's kind of the theme of the concentration blob. right? And then the third one. So this, yeah, this is the thing about this is the Dowd cotton model for these kind of dendrimer, these kind of branched polymers that have chains that go out. So they're concentrated in the middle, less concentrated on the outside. You can say they're composed of these blobs. I can see this blob theme went along pretty well. This is, I don't know what year this is. It's probably hidden under this. Yeah, 82. So it's like 70s, 80s. Right? So Dowd and Cotton were two French guys that did this stuff. The Gens is a key player, but in France. But right, then the thermal blob is another one. So there's four. What are there? Tensile blob, concentration blob, thermal blob, and collapsed coil blob, and Kuhn length blob. So there's 5 total. But Kuhn length we already did. We did tensile, we did concentration. There's this one. This is the most complicated of the things, right? So this one is the opposite of the so it's the opposite. So for the tensile blob, it gets on large scale, it goes to 1, small scale is 2. Concentration blob, large scale is 2, it's expanded, it's small because it's overlapped at the large scales and it's not overlapped at the small scale, small n. Tensile blob goes the opposite of that. So you can see it's kind of a symmetry between tensile blob and Kuhn, because this is like an internal force straightens it out. This is an external force straightens it out. And you can think like concentration, it's kind of like a external collapse, and this is an internal collapse. So this is the thermal blob is almost the same idea as the collapsed coil. So the coil wants to collapse locally first because the smaller chains, the entropy is what makes it want to expand. When you have a shorter chain, it has less entropy. So the small chain segments will collapse first because they have less entropy. And the big chains that have a larger n have a higher entropy. In other words, n ln n is a bigger number, and then they'll expand. So the large things, the thermal expanded, small scale, it collapses. And as temperature goes through, this can explain, give you a cartoon for why the Floyd-Kriegbaum thing works, right? So that's the idea of the thermal blob. So the idea is to predict this. So the Floyd-Kriegbaum can predict that gradual change to the theta state, but there's no cartoon of like what happens, like what actually happens in the chain, right? It can give you the size of the chain, but it doesn't say like what happened to it. So so anyway, if this guy, so you have the size of the chain. So at large scales, it's an expanded coil and it's collapsing locally, right? So it's basically you have the number of blobs, which would be the number in a blob. So molecular weight of chain divided by the number in a blob, the 3/5 power, because it's a good solvent chain, times this tensile blob size gives you the coil size, right? And then the number in a tensile blob, because they're Gaussian down to that size, is the tensile blob size over the Kuhn size to the squared. It's like NT, L times NT, L squared times NT is this zeta T squared. So the ratio of those squared, n by that, gives you the coil size if you multiply by this. So if you pile all that together, you get this weird expression that has n to the 3/5, the scaling you want. It's got the tensile blob size to the 1/5 and the Kuhn length to the 6/5, right? Which ends up giving you, anyway, this kind of works out. So you have that expression for the coil size following this cartoon of like the coil being expanded at large scales and collapsed at small scales, right? And then you have another answer. You have 2 answers for this. One, the other answer is a Floyd-Kriegbaum that predicts the curve shape here, right? So we have the answer from before the Floyd-Kriegbaum for R, and then you can equate these 2 R's. And what you find out is n to the 3/5 drops out. VC is L cubed, so this is to the L to the 3/5. Then L to the 2/5 gives you 5/5. This is 6/5, so you end up with L to the 1/5. And you also have this blob size of the 1/5. And then the ends have canceled out, and you just have this guy to the 1/5. So if you take that, you just get that this thing's the Kuhn length divided by 1 minus 2 chi, which is 1 over t. Chi is 1 over t. So
this gives you like a temperature dependence to the blob size. Right, so it gives you a cartoon of how the coil, how that locally collapsed coil, as the temperature goes up, expands out until the entire chain becomes a Gaussian chain. So it gives you allows you to give a cartoon of like how that structure can change. And it's the same theme, like you put a perturbation onto the chain, and it like introduces a new size scale. So they don't, because it isn't just a small molecule, and because it's n dependent, all the features on it, then basically as n changes, you get different behavior, and there's a transition point where you go from the good solvent to the theta solvent. Right. So anyway, so that's kind of how that works. If you draw that out, and so a scattering picture of this is kind of useful. So because it's hard to draw these cartoons of these things. And the scattering just gives you these scaling laws, and this whole thing is built on scaling laws. So if you like log intensity, log Q, so you're always going to have this Kuhn step at the highest end, right? This -1. And then where that transitions to a steeper slope, that's where it starts to kink up. So it gets a higher dimensionality because it's kinking up. Right. So if you have a thermal blob, it's going to kink up into this 2 slope. Then you have the transition size, so 1 over the blob size. Then it goes to good solvent at large scales. And then you get the coil size here. Right. And as you change the temperature, this thing moves to the left. So it gets to eat up more and more of the chain with a steep slope thing. Right. So as the temperature decreases, I mean, towards the point where it becomes a theta temperature, then it would be all -2. Right. Like this number, so the number here doesn't change. That's basically the number of units times the concentration of the units. So number of units squared, number of Kuhn units squared times the concentration of Kuhn units is what this number is. And that number will be like flat. So you can think of, so that number doesn't change as you go through this temperature change, but this thing will go up. So you can think this 2 just reaches up to that point, and you can kind of see that the coil size will be here. When it was Gaussian, when it's expanded coil, this 5/3 just drops until it reaches the Kuhn length. So the coil size would be like over here if it was expanded. And this is 1 over size, that's a larger size. Right, so you can kind of get a picture. So that's what they call an inverse space picture of what's happening. In some ways, could be easier to understand if you figured out what was going on. And then concentration blobs the opposite way. Like the 2 is at the large sizes, and the expanded coils at the small sizes. And as you increase concentration, the 2 eats into this more. So the 2 kind of moves over. Coil gets smaller, 2 gets, so you can figure out the totally Gaussian chain will be like here. Right, and the totally expanded chain will be over here. So that's a picture scattering for that. And then the tensile blob one, you pull on it, and the R gets larger. This number here stays constant, but basically the one would drop until it actually meets the Kuhn one, and the whole thing would be 1. So just shoot out over here, and that would be the coil size. And then as you take the force off it, the 5/3 would extend up until it reaches that point. So this intercept, the 0 intercept stays the same. The Kuhn size stays the same. The stuff in the middle changes as you put different perturbations on the chain, and you introduce this new size scale to account for that. Right. So anyway, so that's what we got. We got like 5 different ways to mess with a polymer chain, right? I mean, and the Kuhn length we talked about extensively, and then tensile blobs, kind of a simple thing. Temperature, concentration, and this collapsed coil business. Right. So it's kind of like 5 different of these blob things. I think you could probably invent some more if you came up with new things like electric field blob or something, right? But basically those are the ones people talk about. Yeah, the next thing is kind of involved. So like 10 minutes. I don't know. I can just introduce the idea. Like one of the first things where they worked in this, like the concentration blob. Okay, there was some issue with this with the osmotic pressure. So there's a dependence. So you can plot the osmotic pressure divided by concentration versus concentration. So how is that supposed to behave? So the osmotic pressure, this idea that you have, say you have solvent, so you have like toluene and then polystyrene and toluene, or this could be like salt and fresh water, right? So it can be any kind of colloid. And then these things, the black beads want to reach equilibrium, like they want to have constant concentration across this, but the membrane doesn't let the black beads pass through, right? So that means that this toluene over here wants to dilute the polystyrene. I mean, it wants to have a uniform concentration. It can't actually reach it because it's like gravity pushing down on this. So basically it'll squeeze the liquid over into this to try to dilute it. And that raises the level of the liquid here. Right, so there's a pressure head. That pressure head is related to the well, it's related to the molecular, the concentration of the beads here and the KT. So PV is nRT type thing. So that's like an ideal. So you can say the black beads in an ideal situation are like a gas atoms bouncing around and they create a pressure, they create that pressure. It's called the osmotic pressure. So it's the same thing that makes your fingers wrinkle up in the ocean, like the osmotic pressures driving the water out of your fingers and making the skin crinkle up. Right, so this is pretty common. So osmotic pressure becomes like a standard thing, and then once you call it pressure, then you can just say it's the same as pressure, like a gas pressure, and this is like an ideal gas. Or you could say it's got this Taylor series expansion, it's got a second Drill coefficient, right? So you just take all the laws about gases and you just plop them into colloidal solutions. Right? Everything you said about gases, that's why, so everything starts with something simple like van der Waals. And like everyone tries to use that simple thing to explain everything else, right? So it's like gases, pretty well known, colloids less so. And you just say, well, colloids are just a gas. It's just kind of a gas because each of these things is moving around by KT, just like a gas atom. So you have the same ideal situation, the same kind of power series expression, same P2, the same excluded volume, the same enthalpic interaction, attraction to make the phase separation happen. Right, so you just take that and lift it and just say the same thing about it. Right, so in fact, when you look at oops, wait, that's what I want. So so when you look at this intercept, so like in other words, I said the intercept depends on the interactions, right? So basically you're measuring. So what if you have just a glass of water and you shoot a beam of light through it, you get some scattering, right? So what causes that scattering? So the atoms, the water atoms are moving around with KT, and then they're randomly moving around like the stars. They'll be like clusters of stars, right? It's a constellation. And then there's blank spaces in between the stars, right? So that's a random distribution of white dots, right? So a random distribution has like clusters and it has white. And this osmotic pressure, again, it wants to dilute the clusters. It wants them to spread out, right? So osmotic pressure is what's driving the thing to be uniform. Like whenever it clusters, it wants to dilute it. And whenever it's diluted, it wants to concentrate it. So it gets a flat concentration across it. The thing that's making it want to fluctuate around is the KT. So it's like a battle between KT and this osmotic pressure that gives you scattering from a glass of water, right? So whenever you see the flat thing and scattering, that's like a glass of water. It just sees like a shirt. Oh, you see the shirt. You don't see the fibers, right? Unless you go to small scales, you can see the fibers. So basically that's going to be a measure of the change in the osmotic pressure with concentration, the derivative of it. This number, this intercept of the I over here is going to be 1 over the derivative of the osmotic pressure with concentration. And if you go back to the osmotic pressure thing, so the first derivative of osmotic pressure is the second virial coefficient. In other words, this term, because it's going to be pi by rho, that term drops out and you just get B2 for the first derivative. So this intercept on this plot gives you B2. It gives you 1/B2. Right, so that's an easy way to measure B2 as a function of concentration. You change the concentration, just measure that intercept, and then you can get directly the thermodynamics from how bright the light is. Right, so it's kind of like anyway, so all right, because this is going to be a little bit extended to go through this. So why don't I quit there? Like we don't really need to go through more of that, but anyway, so but there's a, I'll show you that there's an application of the concentration blobs and understanding osmotic pressure dependence on concentration. That's one of the seminal things people did. So kind of in the 80s, 90s, but all right. Oh, all right. Next week I'm not going to be here. I got to go to a meeting. So I might have someone come in, or I might do a Zoom, like just do the class on Zoom. But I'll be here on Friday, the day before spring break, to give a paper to do, so anyway. So Monday, Wednesday, I won't be here. I may get someone, or probably may just do a Zoom call, so.
I'll lunch in on like the start before the break, will that be? Tuesday or will it be to like after?
No, after.
Okay.
Yeah, after.
Cause I don't want to bring it.
Yeah. All right. Yeah, I want to give a homework because it's good to have one every week. It's kind of bad to give one over spring break, but I don't know. It kind of works out that way.
Well, I have a professor doing this.
Oh, that's nice. All right.
It's my reactions.
Oh,
Reactions class. It's physically. No. I don't have that.
is it?
Oh, okay.
Uh,
Yeah, no. No, yeah, okay. I hope whoever is teaching reactions. He's like fine, but apparently like if they have the old exam that he had, so like now he's making your class so it's kind of harder, cause like the idiot just copied the answer sheet.